Hello everyone, my name is Jingyi. This is my partner Mehrnoosh. We are making this video for ECE551 course final demo.
Okay, so now I want to go through the Verilog codes that we have for our soft core microprocessor, and here you can see basically the top module for our processor, and here this is the definition of inputs and outputs, and you can see the register definitions here, and after that we have the wires definition. And here is basically how we decode the instructions which are coming from RAM data. So we got all these, like the range of these bits and everything from the ARM instruction set, because we wanted our processor to be ARM compatible. So this is basically the 21 operations that we can support in this microprocessor. And after that, this is where we implemented shifting operations, because in a couple of these 21 operations we have like some shifting operations going on, so we needed to implement this. So these are our shifting, and after that I'm gonna show you the arithmetic logic unit, or the ALU. So the ALU, or the arithmetic logic unit, is in charge of implementing the addition and subtraction for on both registers, or the direct operands that we're passing. And after that, there is something really important about addressing modes in ARM architecture, which is it can support 7 different working modes, and these are user mode, system mode, supervisor mode, abort mode, fast interrupt mode, internal interrupt mode, and undefined mode. And when the ARM processor starts, it first starts its execution under the supervisor mode. Then in this mode, it can access any resources in the system. After that, it will modify the value of a register called CPSR_M to change its working mode from supervisor mode to the system mode. Basically, they're kind of like the same. The difference between user mode and system mode is under user mode you cannot access all the resources. Also, you cannot change its working mode by modifying the value of CPSR_M register. Under user mode also, if you want to switch working mode, you have to execute a software interrupt to enter to supervisor mode. So as you can see here, we have like all the register values for these 7 different working modes. So basically, if I want to show you what we have in the code, I have to go to the part that we want to detect the addressing mode, and we want to detect, so it's here. Basically, by using this code, we want to see, as you can see here, the register 8 is different here. If you're in system and user mode, it's gonna be R8. Otherwise, if you're in fast interrupt mode, it's gonna be R8_FIQ. So by getting this line, I can detect based on the CPSR_M register value in which mode I am, and then I can basically define the values. I can get and translate the values which are inside my registers. Alright, after that, this is the UART, or serial port source code, Verilog code that we have, that I'm showing here. After that, we use the Altera IP RAM and ROM modules. So this is for the RAM, and also this is the source code for the ROM. And this is basically the really top module that is connecting everything together, both the serial port, RAM, ROM, and the software microprocessor all together. First, we have to go through the startup.s, which is an assembly file for initializing the whole environment. So as you can see here, we're gonna call the main, and by this main I mean the main function in the hello.c, which is a file we want to execute on our cross compiler. So it's basically just a simple printing of a string hello world. And in retarget.c we had to retarget our fbootc, and we had to add this file stdout, and the reason for that is because every time the standard library, when we call printf, we want to print to console, but here when we call printf, we want to print everything to the serial port. So here we had to retarget the fbootc to be able to do that. Serial.c contains all the serial port routines, and as you can see here, there are like mappings of different addresses for serial import, serial output, and also the serial flag. And if we get back to arm.we, there is a place for receiving the information, which you can see that's basically for serial in, and the address is exactly identical to what you can see for serial import. And the serial output is 4. So as you can see here, again in the code, when we want to send something, the address that we use is exactly identical to serial out.
As you can see here, this is Ultra Cyclone 4 development board we use for developing our soft microprocessor. You can see this pin is connected to the TX of our Arduino board. Because we don't have the serial port to USB converter, so we have to use Arduino as a kind of bridge for helping transforming data from the FPGA to the host PC.
Okay, now let's see how we compile the whole design. First of all, we have to build the files. It's going to generate a file called hello.bin, which is a binary file. Then we have to convert this binary file to memory initialization file, so we just copy that. And we will remove it to a program called bin to mif converter. So we just use a command to execute this bin to mif converter, and this is the final name for that mif file, that mif. And also we have to enter 32 for quarters, and then when we execute it, as you can see, it just creates the final demo hello.memory initialization file. After the mif file is generated, we have to copy this mif file to the folder where all the files of our project exists. And then after that, we have to go to Mega Wizard plugin manager in tools, and we have to use the existing custom file, and then we have to choose the rom.we. Then I have to go to memory initialization file, and I have to basically find my memory initialization file here so that it can be loaded into the ROM. Okay, now we have to then compile the whole design. After compiling the whole design, then we have to burn our file into the FPGA. So as you can see here, then we have to start it by burning everything to the FPGA, and it's gonna then print all the strings that we have from the serial port to the serial port debug assistant that is on the PC.
Hello. As you can see here, this is our microcontroller development board. It's the STC microcontroller here, and you can see this microcontroller connected with the 1602 LCD. So you can see the results is displayed on the LCD here. So this is our controller here, the small tiny controller, which is small. And if I press this button here, now you can see it's 45. If I press a button here, it's gonna be 46. I press this button, 47. Press button, 45. So it can finish the decode. So let's see the infrared control code. So at first you can see this is a delay function, and after that is the enable and write function here, because when you display the result to the LCD, we use the 1602 LCD. So when you send all these commands for initialization, and after that, those two functions for displaying string on the LCD. And here is our main function here. So we open an interrupt here, and we display something here, and we open an interrupt, and then we delay, and we do the LCD initialization, and after that we display string on LCD, and here's while loop here, and here comes our interrupt service routine. So this is whenever I press a button on the controller, it's gonna generate an interrupt. So here you can see, because on this microcontroller development board, we use WD6122 chips. So as you can see here, even though it's in Chinese, but I will explain. So it starts from the initialization bit. It's usually consists of 9 milliseconds, and after that is low 8-bit user code, and then is high 8-bit user code, and after that is 8-bit the key code, and after that is the key code's complement. So as you can see here, in our interrupt service routine, we're gonna decode all this and find out which key has been pressed.
In order to test our CPU proficiency and speed, we use the integer and logical benchmark called Drystone, which comes with 2 different C files and 1 header file. As you can see, drystone1.c, drystone2.c. And then what we have to do, we have to first generate the bin file, and after that we have to go to our model sim, and in model sim we have to get this bin file dry.bin as an input, and we have to load it into the ROM. So then the CPU is able to run the instruction one by one from the ROM. Then we have to show how we simulate it. As you can see here, if we run the CPU design using that benchmark, we just set the execution time to 6,000 different runs. Okay, the Drystone results are ready, and you can see that for 6,000 different runs. And finally, you can see the most important metric that they have, Drystone per second. Okay, in this part we use the Micro Center program, which is a program that connects the GPS module with the PC through the USB. And then by getting advantage of this, we can get the exact information of the position of our GPS. So these are the information that are coming from the GPS module. So after that, we then want to compare the results that we're getting from this software with the results of when we connect the GPS module to the controller to see whether they are close enough. Okay, right now we want to compare the results we got from that with the results that we have from the microcontroller that we're connecting to our GPS module. And as you can see here, it's the current time that is displaying, and here is the exact amounts 71 that we're getting from the software that we were using, so it's accurate enough. We use the assembly code in order to control our connection to the GPS module. So at first we needed like one routine, which you can see here, which is in charge of getting all the information from the GPS and try to polish it in order to get the exact location from those information. It was like in a lot of bits in strings, so we had to kind of like polish those information. And also we need to do like some calculations for getting the current location and time, so we used again assembly code in order to do that. A failure that we had is we wanted to use the GSM module and AT commands in order to be able to send out the location information through SMS, and as you can see we used AT commands, but we didn't succeed in getting it working. The reason why we used IAR embedded workbench, that's because it works with Texas Instrument Zigbee module, and also we got the code from Texas Instrument and we just modified it. So as you can see here, there are two different functions. One of them app switch and the other one app light. You can comment and uncomment the other one, and you can switch this comment and uncomment based on whether you want to create a sender or a receiver in Zigbee. As you can see here, there are two different Zigbee modules that they're connected to each other. When you press a button here, there's a light which is on there, and as you can see, there is a light here that by pressing the button on the other Zigbee, it's on and off. Okay, finally, with the biggest failure that we had is getting this card working with our software microprocessor. We were supposed to write a C code and then execute it on our cross compiler, and then in order to be able to execute it on our software microprocessor, we couldn't get it working. So we have the C code and we used Arduino to drive the car drive this car, but we couldn't get it working, and we still don't know the reason, but we think maybe that's the power issues that we have. So maybe in future we can still work on this part and try to get it working with our code. And another thing that we had was so we were not able to provide infrastructure for future upgrades, which was one of the main reasons for the Internet of Things. And the reason why was the Ultra board that we were using didn't support the partial reconfiguration. And also the other thing was we were not able to port an operating system, and that was because we had to manage like a lot of resource management stuff, and we were not able to do it in a limited time that we had.